Hayalperestlerin, risk alanların, denemekten korkmayanların cesaretinden doğduk. Bizi asla yarı yolda bırakmayan o sesin rehberliğiyle ilerlemeye ve öğrenmeye devam ediyoruz. Bunun için varız. Bu yüzden gece geç saatlere kadar lambalarımız sönmez. Elveda demek hem hüzün hem de gurur verir. Her şeyi sorgulayarak ve merakımızı besleyerek, dayanıklılığımızı test ederek, sınırlarımızı aşarak, ilerleyerek ve yeni ufuklar açarak yeni bir yol buluruz. Yeni icatlar çıkararak, kendi yolumuzu çizerek. Burası fikirlerin doğduğu ve yeni fikirleri doğurduğu, bizim de doğduğumuz, birlikte büyüdüğümüz ve yükseldiğimiz yer. Burası Yakın Doğu Üniversitesi.
Hello everyone, dear colleagues. Welcome to Third International Conference on Water Problems in Mediterranean Countries and Sixth International Conference on Natural Resources and Sustainable Environmental Management. This is Room 2, Session 3. We have a couple of researchers who are willing to present their insights in their research, and each researcher will have 15 minutes of time allocation. Our first presenter is Dr. Mullah Gariba Sharon.
Good day, ladies and gentlemen. The hydraulic fracturing process, if not properly controlled, can be detrimental to the environment. Hydraulic fracturing or fracking has generated more than 280 billion gallons of toxic waste since 2012. It has produced up to 450,000 tons of air pollution yearly, and it has degraded more than 360,000 acres of land in the United States since 2005. My name is Mullah Gariba Sharon, a PhD student in the Department of Petroleum and Natural Gas Engineering at Near East University. Today's topic is titled Effects of Frac Fluid and Proppant on the Hydraulic Fracture Geometry and Production, a Taylor Sandstone case in Texas. I'll start by giving a brief introduction and literature review, followed by the methodology, and lastly, the results and conclusion. So what do we really understand by hydraulic fracturing? It is a well stimulation technique that is used in unconventional and tight reservoirs in order to improve productivity by pumping sand, water, and other chemicals downhole into the reservoir at high pressure in order to break the rocks so that oil and or gas can easily flow from the reservoir into the wellbore. The original work was done by Robinson and others in 1992, where they evaluated the hydraulic fracture performance in the Taylor Sandstone reservoir using a single layered model. In 2016, Shaw and others utilized a multi-layered model to improve long-term gas production. In this study, the main goal is to assess and compare the effects of different fracturing fluids and proppant on post-vertical gas well performance in the Taylor Sandstone reservoir using a fracture simulator known as FracPro, and to compare net present values using simulation of prop hydraulic fractures for various scenarios. The Taylor Sandstone reservoir is a thick upward coarsening sequence made up of sand, siltstone, and shale that were deposited on different depositional environments as shown on the figure. As we can see, the reservoir quality decreases drastically in the lagoon deposit. The methodology was done as follows. Firstly, we carried out a detailed literature review for all petrophysical and reservoir properties, followed by designing hydraulic fracture treatments. Thereafter, we ran a parametric study and conducted a post-fracture production analysis. And lastly, an economic analysis was done. The table shows the reservoir properties that were used in modeling the hydraulic fracture. 16 different scenarios were used in this study. We have 4 different perforation intervals that were defined by their perforation lengths, 20, 40, 80, and 100, 2 types of fracturing fluid, slick water and hybrid, as well as 2 types of proppant, sand and ceramic proppant. A proppant is basically a solid material that is pumped downhole together with the fracturing fluid in order to keep the fractures open. 2 types of treatment designs were used in this study, slick water and hybrid fracturing. Hybrid fracturing is basically a combination of 2 different types of fracturing fluid. In this case, we use slick water and 20% linear gelled water. We use the same sizes and types of proppants for both designs in order to be able to compare their fracture geometries as well as productivities. Slick water was pumped at a rate of 80 barrels per minute, while hybrid was pumped at a rate of 50 barrels per minute. The figures show fracture geometry for scenarios 4 and 12. The fracture geometry of a hydraulic fracture is basically its height, its half length, and its width. The fracture half length is very important in productivity, and it is the radial distance from the wellbore to the outer tip of the fracture. As we can see, the upper fracture utilized slick water and sand, while the lower fracture utilized hybrid and sand, both at the perforation length of 100 feet. We notice that the lower fracture is much longer compared to that of the upper fracture. So from this, we can predict that the lower fracture is going to produce more gas compared to the upper fracture. Here we have fracture geometry for scenarios 5 and 13, both at the perforation length of 20 feet. The upper fracture used slick water and ceramic, while the lower fracture used hybrid and ceramic. So from this, we can say that different fracturing fluids, different proppant types, and different perforation lengths can produce different fracture geometries, which in turn we have different productivities. Here, we're going to discuss the effects of perforation length, frac fluid, and proppant types on the fracture half length for hybrid and slick water frac. From the graph, we see that the fracture half length increases as we increase the perforation length. We also notice that hybrid fracturing produces much longer fracture half lengths compared to slick water frac. This can be explained using Stokes' law. Hybrid fracturing consists of a linear gel that increases the viscosity of the fluid, which helps to limit the proppant carrying capacity, thereby depositing the proppant further into the formation. For slick water frac, all the scenarios that utilize sand proppant show slightly longer fracture half lengths compared to the scenarios that utilize ceramic. But the reverse was true for hybrid fracturing, except for scenario 11. Here we have fracture height versus perforation length for slick water and hybrid fracturing. At shorter perforations, taller fractures were produced. This is because shorter perforations increases the friction of the formation, which pushes the hydraulic fracture upper and extending its height into the caprock. This phenomenon can be very detrimental to our environment because it can break the cap rock, which can lead to seepage of the fracturing fluid into the surrounding aquifers, which can degrade the quality of drinking water. And as we can see on the graph, it is more severe in slick water frac compared to hybrid fracturing. Also, all the scenarios that utilize diamond lightweight ceramic proppant show taller fractures compared to the scenarios that utilize sand. But it was expected that sand shows slightly taller fractures compared to diamond lightweight ceramic because sand has a lower specific gravity. It is very important to control the hydraulic fracture height, like we discussed earlier, because it can destroy the cap rock, which can cause seepage of fracturing fluids into the surrounding aquifer. The stress differential between the reservoir interface and the surrounding strata is very important in the containment of the hydraulic fracture height. So therefore, the hydraulic fracture was supposed to be contained within the reservoir interface. But because of shorter perforations, we see that the fracture height was extending into the cap rock. But at longer perforations, the hydraulic fracture height was contained. Here we have the fracture width versus perforation length for slick water and hybrid fracturing. For hybrid fracturing, the fracture width decreases as the perforation length increases. It was difficult to quantify the effect based on viscosity alone because the formation could not accept higher injection rates for hybrid fracturing. So therefore, we can say that slick water frac produced wider fractures because it was pumped at a higher injection rate. In a study conducted by Perkins and others in 1961, they found that the hydraulic fracture half length can affect the fracture width. In this study, we see a very good correlation between the fracture width and the fracture half length. And from the graph, we notice that the fracture width decreases as the fracture half length increases. So we can say that slick water produce broader fractures because of their shorter fracture half lengths, while hybrid produce smaller fracture width because of their longer fracture half lengths. The chart shows dimensionless conductivity versus proppant. From the chart, we notice that all the scenarios that use diamond lightweight ceramic show higher conductivities compared to the scenarios that utilize sand. This is because diamond lightweight ceramic have controlled size particles and shapes, whereby sand have irregular size particles and shapes, thereby leading to a tight packing arrangement, hence reducing conductivity. The table shows gas production forecast after 10 years for all 16 scenarios versus a case of no hydraulic fracture. From the table, we notice that for the 4 different cases, the perforation length of 100 feet had the highest gas output. The graph shows cumulative production versus time for the 4 best scenarios used in this study compared to a case with no hydraulic fracture. As we can see, scenario 16 had the highest cumulative gas production of about 1.354 billion cubic feet. We're going to discuss the effects of propped half length and fracture width on cumulative gas production. The first graph shows that cumulative production increases with an increase in propped fracture half length, while the second graph shows that cumulative production increases with a decrease in fracture width. The tables show comparison of material costs for sand and diamond lightweight ceramic for slick water fracturing. We can see that the cost for diamond lightweight ceramic is more expensive compared to that of material costs for sand. Here, we have a comparison of material costs between sand and ceramic proppant. Also, the analysis shows that diamond lightweight ceramic is more expensive compared to that of, sand. And we also see that hybrid fracturing is more expensive compared to that of slick water frac. Here we have the table for a comparison of net present values and rate of returns for the 16 different scenarios. The net present value in this case tells us which scenario is more profitable. The higher the net present value, the more profitable the project. And from the table, we notice that scenario 16 is the most profitable. In conclusion, hydraulic fracturing is an efficient technique to improve productivity in tight reservoirs. The fracture geometry depends on the rock mechanical properties, fracturing fluid, proppant types, and the perforation length, while production analysis depends on the fracture half length and the amount of proppant in the fracture. These are my references. Thank you for listening. Any questions?
Thank you very much, Dr. Mulagari Basharan. Any questions will be directed to your email. So thank you for your contribution to this conference. Next is from Dr. Miriam Deras.
Our presentation revolves around the circular economy metrics for sustainable energy harvesting. I'm Maryam Darraz, PhD student, and together with my esteemed professors Shuaib Nawawi, Mehdi Ladisi, Abdouahid Hijaji, and Azzdin Azim, we've been dedicated to this work. Operating from the Laboratory of Engineering Sciences for Energy at the National School of Applied Sciences, Shuaib Dukal University Al Jadida, Morocco, we are excited to share our insights and advancements in the field of piezoelectric materials, synthesis, and characterization. Our focus centers on the chitosan extraction film, a highly promising polymer matrix for piezoelectric materials. What makes this matrix truly exceptional is its origin from recycled maritime residues, specifically shrimp shells. In our presentation, we will delve into the extraction, preparation, highlighting its potential as an environmentally friendly matrix, where this chitosan-based matrix, enriched with piezoelectric ceramics, becomes a key player in transforming mechanical energy into electrical energy. It's a sustainable step toward a greener future. precipitate was washed and dried in a chitosan powder or flakes. Finally, the obtained chitosan was stored at 5 degrees Celsius until use. Moving now to the chitosan film preparation. The chitosan film preparation involves dissolving chitosan powder in a 2% acetic acid solution, stirring for 6 hours, casting onto petri dishes, and then drying at a room temperature. Moving now to the chitosan characterization. In the following figure, we delve into the Fourier transform infrared spectroscopy absorption spectra of chitin and chitosan. Both spectra indicate the presence of hydrogen bonds, with chitosan revealing a less ordered structure. Shifts and variation in certain absorption features suggest changes in molecular vibrations, emphasizing structural differences. Notably, the absence of specific bands in the chitosan spectrum signals transformative shifts, indicating the impact of the decitylation process on the polysaccharide's structure. For the X-ray diffraction of the prepared chitosan, the diffraction peak located at about 20 degrees is broad and poorly defined, which means that the prepared chitosan sample is poorly crystallized. Chitosan is mainly characterized by its molecular weight, which is an important parameter for a number of its physicochemical and biological properties, such as hydrophilicity, viscosity, water absorption, biodegradability, or biocompatibility. Molecular weight determination was determined from the intrinsic viscosity by applying the Mark-Wink equation. The molecular weight value found for this prepared chitosan is equal to 700 kilodalton, which is relatively higher than those generally given in the literature. And this is probably due to the mild treatment used for the decitylation of chitin. Chitosan is the partially decetylated from chitin. The ratio of decetylated units in relation to the total number of units is called the degree of decetylation. The term chitosan applies to any copolymer with more than 15% decetylation degree. And in order to accurately determine the degree of decetylation of the extracted chitosan sample, 3 different methods were utilized. The first method is the conductimetric titration, then the pH nitration pH second derivative method, and finally the infrared spectroscopy. These methods, or by using multiple methods, we can obtain a more comprehensive understanding of the degree of decetylation in the extracted chitosan sample, and the degree of decetylation results obtained by the different nitration methods are shown in this table, and the average value was found to be 77.32%, which is a good decetylation degree. The chitosan films demonstrated the tensile strength of 43.9 megapascal, indicating the maximum stress the material can endure before fracture occurs. Additionally, the elongation at break was measured to be 3.14%, which represent the maximum strain that materials can undergo before rupture. This finding indicates the potential of tituzene films to enhance the mechanical properties of our composites. Thermogravimetry revealed tituzene film's thermal stability with initial 10% weight loss representing moisture evaporation and subsequent 65% loss representing saccharide ring degradation. The DTG curve peaked at 320 degrees Celsius, persisting until 415 degrees Celsius. The differential scanning calorimetry highlighted an 88 degrees Celsius peak, representing glass transition temperature, and the 302 degrees Celsius peak, presenting thermal degradation temperature, implying a two-step process: water loss and tituzene polymer decomposition. To conclude, we can say that tituzene is a promising biopolymer for use as matrix material in composite application. The extracted tituzene possesses several desirable properties. These properties make it suitable for use in various fields, including biomedicine, environmental science, or industry. By controlling the degree of decetylation, the properties of tituzene-based composites can be enhanced, resulting in improving biodegradability, biocompatibility, or even mechanical properties. And our study highlights the potential of tituzene as matrix for piezoelectric composite materials by combining tituzene with piezoelectric materials such as piezoelectric ceramic powder. Composite material with improved piezoelectric properties could be developed. And we can say finally that these composite materials have potential uses in areas such as energy harvesting, sensors, and actuators due to their unique properties. Thank you for your attention.
Thank you very much, Dr. Miriam Terras. Our next presenter is Dr. Ben Said Lubnan.
Hello. Firstly, I would like to thank you for accepting my collaboration with you today in this conference. Thank you very much. I am Lubna Ben Said, a first-year doctoral student at the National School of Applied Sciences in Al Jadida, Shuaib Dukal University, Morocco. Today, I will present to you the following titled, The Comparative Study of Piezoelectric Energy Harvesting Techniques. In this presentation, we will delve into an introduction of the subject, followed by an explanation of energy harvesting circuit configurations. Subsequently, we will conduct simulations of the techniques using LTSpice, providing an interpretation for each method while comparing their performances. Finally, we will conclude with the further work. I hope this presentation proves beneficial to you. Non-linear energy extraction methods have been devised with the goal of efficiently enhancing the energy transfer from a piezoelectric generator to the target load. This involves maximizing the value of the extracted energy by integrating a circuit that facilitates the shaping and storage of the converted mechanical energy into electrical energy. Recent strides in microelectronics and ambient energy harvesting open up the possibility of envisioning the creation of entirely self-sufficient electronic systems. In order to boost energy conversion efficiency, advanced techniques involving nonlinear electronic treatments have emerged. These techniques entail integrating nonlinear elements such as switches into the circuit different from linear scenarios with linear loads such as resistance. This approach aims to effectively manipulate the piezo voltage for enhanced performances. The presentation focuses on proposing diverse methods for energy recovery, particularly emphasizing the use of piezoelectric elements. Techniques include standard DC mode, DC-DC converter, and innovative concepts like synchronous switch harvesting on inductor. Variants such as PSG and SSG aim to enhance energy recovery efficiency, while advanced technologies like double synchronous switch harvesting and enhanced synchronous switch harvesting provide load-independent solutions. The overall goal is to optimize the conversion of vibratory energy into electrical energy, addressing challenges related to impedance adaptation and fluctuations. Moving on to the energy harvesting circuit configurations, we will start with the standard circuit. In the conventional interface circuit, a diode rectifier bridge is directly linked to the piezoelectric element, followed by a filtering capacitor CR and the load RL as illustrated in the figure. This configuration represents the most basic circuit for rectifying an AC voltage and is widely employed in energy harvesting applications. The rectifier bridge is considered idle and the resultant rectified voltage VDC is assumed to remain constant, which is reasonable approximation when the time constant RL multiplied with CR is significantly greater than half the mechanical oscillation period. In determining the output power, we assume that the mechanical displacement U follows a sinusoidal wave and the open circuit voltage V on the piezoelectric material also exhibits a sinusoidal pattern. In this method, the diode rectifier operates in a blocked mode, maintaining the piezoelectric element in an open circuit when the absolute value of V is below VQR across the capacitor. As soon as the value of V exceeds the VQR, a current flows through the capacitor and then to the load. The generated power is the energy produced in a period T, calculated by integrating the product of the voltage and the current over one period. The drawback of this circuit stems from the discontinuity of the current flowing to the load and the absence of synchronization with the piezoelectric voltage. As a result, traditional interface circuits are ineffective in this scenario. It's crucial to highlight that the mentioned circuit serves as a baseline and doesn't contribute to enhancing power output. Therefore, additional circuits and network topologies are proposed to augment power generation. Move on to the PSG. The parallel SG interface introduces a nonlinear processing circuit connected in parallel with the piezoelectric element, as depicted in the figure. This circuit comprises an electronic switch with an inductor L connected in series. The switch is predominantly in the open state, except when an extremum in displacement occurs. At that moment, the switch briefly turn on, creating an oscillating electrical network involving the inductance L and the clamped capacitance Cp of the piezoelectric element. As a result, the energy stored in the structural clamped capacitor C0 is released through LC resonance, reaching a minimum value. This action causes an increase in the piezoelectric voltage. The harvested energy in a system employing the SG technique closely mirrors that of a system using a standard interface under strong coupling conditions. Moving on to the SSG. In the series synchronized switch harvesting on inductor technique, the approach closely resembles to the parallel SC method. However, in series SC, the voltage processing device is not connected in parallel with the piezoelectric element and the rectifier input. Instead, it is connected in series, as depicted in the figure. The control strategy for the electronic switch follows the strategy described in the parallel SC case, maintaining the piezoelectric element in an open circuit most of the time. When the switch closes, electric charge flowing through the inductor L transfers a portion of the energy stored in the piezoelectric blocking capacitor C0 to the storage device. Moving on to the DSSH. The double synchronized switch harvesting technique is designed to optimize energy harvesting by accommodating varying loads. It ensures a consistent harvested energy output despite load fluctuations and incorporates intermediate energy storage through a capacitor. This allows for effective control of the trade-off between energy harvesting and the damping effect of the extraction process, ultimately optimizing output power by decoupling extraction and storage units, with YC representing the overall efficiency of the converter and YInt and XInt represent the natural angular frequency and the damping coefficient of the system. In summary, it's clear that the harvested energy is not dependent on the rectified voltage VDC, making it independent of the load resistance value RL. Moving on to the simulation of energy harvesting techniques, we will start with piezoelectric modeling, especially modeling of the piezoelectric source. The deformation of piezoelectric membrane leads to the polarization of the piezoelectric material and the proportional charge transfer corresponding to the applied stress. We employ LT-SPICE to simulate piezoelectric energy harvesting techniques by incorporating a rectifier that supplies a constant direct current source IS. The objective is to acquire a comprehensive understanding of the system's operation and calculating the harvested power in a steady state. This step is vital for comparison and comparison of the system, especially considering the challenges associated with the current measurement in practical scenarios. As you can see, for the standard circuit, here we have this figure shows us the composition of the standard circuit. Here, as you can see in both figures, the input piezoelectric power and the output power of the standard circuit. To assess the performance of the standard circuit, we compare the recovered power to the input power. In this case, we found Pout equal to 6.33 milliwatts, while the input power is 25.39 milliwatts. From this, we observe that the standard circuit doesn't effectively increase the recovered power. Moving on to the PSG. This figure illustrates the composition of the PSG in LT-SPICE for a load represented by 100 kilo ohm resistor. Here we observe the output power, and here we have the piezoelectric input power. The gain of this circuit is calculated by this equation. Here we found through the simulation that the PSG technique has a gain of 750%. In other words, this technique allows for an energy recovery of over 700% compared to the standard circuit. Moving on to the series SC. As we can see in this figure, the composition of the series SC circuit in LT-SPICE. Here we observe the input piezoelectric power, and here we observe the output power. The gain of this circuit is approximately 730% compared to the standard circuit. Thus, it's evident that series SC enables significant energy recovery compared to the standard circuit. Moving on to the DSSH, here we have the composition of the DSSH techniques. The figure shows the input piezoelectric power, and here we observe the output power. We notice from the gain that the DSSH techniques recover 600% power compared to the standard circuit, independently of the load. In other words, for several load resistance value, the power recovered is independent of the load. It's evident that all the mentioned configurations show improvement in energy recovery when compared to the standard technique. Specific gains are defined for each configuration: over 750% for PSG, 700% for SSC, 600% for DSSH, and 400% for SECE. In the case of the DSSH techniques, despite not having an optimal resistance, it facilitates effective recovery regardless of the frequency of variation. In summary, the conclusion underscores that energy recovery topologies involve aspects such as signal detection, switch operation, inductors, complex circuits, and optimal load. Even load-independent systems like DSSH and ESSH have an optimal load region due to the oscillations and circuit losses. The conclusion highlights the delicate balance between feasibility and achieving a high power harvest, emphasizing the significance of discovering an energy recovery circuit with a simple topology and robust energy recovery capacity. The new work will focus on an in-depth exploration of the DSSH techniques and analytical study of a buck-boost converter for piezoelectric energy harvesting. Here you will find the list of references. And finally, I would like to thank you very much for your attention. If you have any questions or remark, I will be happy to discuss.
Thank you very much, Dr. Bensay Lubna. Our next presenter is Dr. Eli Marusi.
Hello, everyone.
Hello, Doctor. We
I
can
hope,
perfectly see you.
sorry?
We can perfectly hear you and see you.
Oh, thank you very much. Can you see my presentation?
Not right now. If you present it from downwards by using the share screen button.
Okay, so I'm going to share screen. Oh, no, that's another door. So just a moment, sorry. Can you see my presentation now?
I think we cannot. If you click the share screen button, then you need to select it from the window section. And then I think, yes, right now we can see it. Yeah.
Okay, thank you so much. So just a moment. Is it okay now?
Yes, it is perfect.
Okay,
All right.
okay, thank you so much.
By the way, Dr. Eli, sorry for interrupting. You can try to full screen it so that we will be sure.
I already full screen it. So just a moment. I think just a moment. Svičala sam, trebala staviti drugi screen. Samo ovako mogu napraviti. Samo kako to mogu napraviti. Just a moment, sorry.
No worries.
Okay. Znači, ovo bi trebala staviti ovdje, je tako? I ovo ovdje. So, is it okay now?
Can you show us your presentation?
It is on my screen, I can see my presentation, so I don't know what is wrong.
We actually cannot see the presentation right now.
Okay, so
But if it is okay, you can, right now, yes, we can see your presentation. You are on the page 4.
and
If you,
is it presentation mode or is it just, you know, with slides?
if you don't mind, you can present it like that by skipping slides one by one, by not being in full screen.
Okay. Sorry for that, but let's start the presentation. I hope nobody is caring about that. So once again, hello everyone. My name is Eli Marušić and I come from the University of Split, Faculty of Maritime Studies, along with my colleagues Igor Vujović and Joško Šoda, also my colleagues at the Faculty of Maritime Studies. So in front of them, I am presenting the topic relationship between marine and coastal resources and revenues in nautical port system. So for the introduction, just a few words that natural resources are vital for developing and sustaining nautical ports and the sector of nautical tourism. So also what is important that there is a major growth in nautical tourism worldwide, and that triggers increased use of natural resources, here marine and coastal resources or land resources, and also expanded nautical infrastructure. Also water surface area or sea area, then the coastal area or shoreline area, and the length of the developed coast equipped for berthing services, here wet and dry berths, are critical parameters for the operations of nautical ports. Also, nautical infrastructure for essential services, berthing and berth-related services comprise most of the port's total revenues. So here we know that those are the transit berthing services and annual berthing services. So this is a little bit like introduction to our analysis, what we have done here in the paper. So here we investigate the visible and hidden correlations between the vital infrastructure of the nautical port system and the natural resources used with the revenues generated by vessels in transit and vessels at annual berth, or sometimes we call all year-round vessels. For this research, we collected the data from the Croatian Bureau of Statistics. There is a lot of data, of course, so those data refer to the capacity and performance of nautical ports as a system. And we collected the data from the year of 2005 to 2022. And here is our research framework. So after the data collection, so there, as I said, there is a lot of data, a lot of information in those statistical sites. However, we selected some that are referential to our research. And after the collection, we selected the data, and then we classified the data into the 4 main groups here that are relevant to the research. So the first group is marine and coastal resources. Of course, there are different variables in the group. And then the group 2, nautical ports infrastructure and nautical demand, the group 3, and the 4th group is related to the revenues. And then we created an analytical framework comprising of different statistical analysis methods, and also here is the results also. So for the first step, we performed Pearson correlation related to the in-group variables. So we try to put into the correlations the variables that belong to the similar or the same group. And also what is important, we classify or we analyze different periods of time from 2005 to 2022, observing that there were great differences between different time periods. And therefore here we presented only a few, like from 2005, 2022, then 2005, 2019, 2008, 2022, and 2008, 2019, and more, of course. Why? Just to mention, like a COVID period that affected a lot the industry, for instance, nautical demand, so that affected also correlations and intercorrelations between the variables examined here. And then, so for each group, as you can see, we performed the similar or the same analytical framework or methods. And then, due to the results that we gather from the first step, we performed another analysis. So analysis is intergroup correlations for all the variables. And that was the basics to conclude, to have some conclusions related to the relationship between the marine and coastal resources and revenues. Of course, to mention, there were more variables in the analytical framework, like employees, but here for this presentation is not relevant. So also to mention, not only the correlations between the groups and into variables, also we performed ANOVA analysis for the variance analysis. And now we have, like, after data collection, we classified the variables. Actually, it was the same step, if I can say that way. So the group 1, marine and coastal or land surface area, it is representing the usage of natural resources. So we have 3 different variables: water surface area, land surface area, and length of shoreline for berthing. And here are the years, also some statistical measures like minimum, maximum, average, and standard deviation we perform for each variable and each group, of course, over the course of time. As you can see it here, there were some, just optically looking at this, there were some big changes. For instance, in the 2005, 2008, and 2007 related to the land surface area. So that was our consideration in creating those time-related groups, as we call them so. And the second group is the nautical port infrastructure. Here consists of the nautical ports, which are of course different. So when we say nautical ports, there are different ports with different performances and operation modes. But however, we selected therefore 2 important variables, like total number of wet berths and total number of dry berths, which are basic services or basic infrastructure for basic services in nautical ports. As we know, nautical ports or nautical tourism ports, sometimes we call them marinas. Also, we can name anchorage. Boat storage is also in this group because it has these dry berths, and so on. So also what we can notice here, that the total number, like absolute number of the dry berths and wet berths, is really very different. So then we have nautical demand. We looked at the nautical demand for the same period and the time period groups with variables connected to the vessels in transit, which refers to the vessels that stay sometimes 1 day or more days, but mainly in the season. So season that starts in April, ends in October. And of course, we have annual berth vessels that have nautical ports, mainly marinas, as a home ports. So they stay over the course of time as 1 year or more, or less than 1 year, but they have different contracts. So we have, like, for those 2 categories, we have different components or data. One is for wet berth and another is for dry berth. So for both categories, to check the hidden and direct correlations. And then we have revenues. Revenues is also a complex variable that consists of different revenues. Basically, as you can see it here, revenues that comprises the majority of the total revenues are those of the birthing services. So here is the total revenue of birthing services, consisting of the two previously explained, birthing for vessels in transit, and then for vessels in all year round, all annual birthing. And then we have revenues for both repair and maintenance services, but as a majority after the first category, and then other revenues. And in total revenues, so we have also those basic statistical measures for all those variables. And now we can see the revenues share of the birthing services, just to mention what I mentioned at the beginning, that the majority of revenues for this nautical port system, or nautical ports as one organization, comes from the birthing services. So it's really high, ranging, you will see here in 2007, for instance, like 76%, 75%, to mention a few, and then the lowest is not below the 68, or, so it's around 70%, which is really important data. And then we have interesting to look at those relationships. Is important to check for the growth rate for each variable and each group. And then also we saw this the situation that the growth rate is changing. So we have a major decline, and there is a growth in the variables over the course of time. So here is an example for the first group, that the 2008 is in some groups excluded due to the major changes, which is not, of course, for this why that happened in external and internal environment. But however, it is important to pick up the different time period groups. And now we have here also the group 2, nautical port infrastructure. As we know, that refers to the berthing system, dry berth and wet berth, and nautical ports in general. So there is a variety of the changes in the growth and decline. And then the group 3 is vessels in transit. So, for instance, we can see here the big major shift is related to the COVID period. So therefore, we excluded the year of 2020 for the correlations or relationship between the two variables examined analysis. And then the group 3, annual birth, also kind of differences. So we can see the group 3 is annual birth. So the prior is the transit, and those are both in the group 3, the differences. And then the group 4 are the revenues. And what we can also see here, that to identify different, firstly, we identified the periods between the 2005 and 2022 to determine the correlations between all variable groups, from group 1 to group 4. And according to our analysis, to the research framework, we concluded, or we identified, that the period of 2009 to 2019 maybe is the best to look as a general period to set the interrelationships between the variables, because other periods are very they bring a lot of changes between the variables, so they will sometimes mislead us to some conclusions. So now we have to investigate the hidden correlations by applying ANOVA analysis for the identified time period of 2009 to 2019. And now, so we can see the data here for the groups like 2005, 2020, 2005, 19, 2019, 2020, and 2009, 19. And from this, we can conclude that the group 1 and the group 3. So group 1 is the group related to the coastal and marine resources, and the group 3 is related to the nautical demand, are very highly sensitive to the time period. And also group 3 and groups 4 are not so sensitive. So that indicates that the period of 2009 to 2019 is the most representative for developing the general analytical framework. Also, this methodology that we used here can be applied to different systems, of course, and different years. And then we also created here the correlation mapping matrix visually for the presentation. Is interesting too with those colors, because those colors represent actually, or the boxes or the cells in the matrix, they represent the correlation between the variables ranging from very strong, which is the most green one, and then the light green is strong correlation. So you can also check the range of correlation, and then we have yellow moderate, weak, and very weak, which bring us to the conclusion that actually this is a very comprehensive and very complex system. Using just these variables bring us to the conclusion that we need to classify those periods in different time period groups to investigate specifics of the interrelationships between the not only research variables but also groups, because some of the variables can be grouped in the different groups than we have done it here, of course. And to conclude the paper, so for this presentation, of course, the paper investigates the visible, once again, and hidden correlations between the vital infrastructure of the nautical port system as an organization and the natural resources used with the revenues generated by vessels in transit and vessels at the annual berth as the basic or major generator of the revenues, as previously mentioned. And also, once again, I'm not going to read all those details here, but just you can check for those groups how they consist of different variables related, of course, to the groups like marine and coastal resources, nautical port infrastructure, that is related to the marine and coastal infrastructure, was important to us, of course, and also nautical demand, which is generator of the revenues, and revenues as a basic business measure or indicator of the success of the company. Also, research analysis and results show that the group 1 and group 2 are variable sensitive to the parameter variations or changes in nautical demand, and group 2 and group 4 are less sensitive to parameter variations. And therefore, the research proposed variable analysis comparing the data for different periods, which is very important, different number of years in the period per period, and the different periods, or we call them time period groups. The dynamic of nautical tourism market is highly competitive and requires profitable and sustainable solutions for managing the resources. Of course, analytical frameworks and analysis, data gathering is of the highly or critical for the managerial decisions. So careful collection of input data, setting research hypotheses here, analytical frameworks are vital. We can conclude that here. Also, here is just a few of the literature that we used for this presentation and the paper. And also, thank you for your attention. I hope this was inspiring to you and bringing you some insights. And for questions, of course, you can ask or
Thank you very much, Dr. Ali Nursi. It was a lovely presentation, and thank you for attending to our conference, and thank you for sharing your insights as well. So,
Thank you so much from Split, from my colleagues. Both of my colleagues actually are with me, so thank you very much for this opportunity. And okay, so see you soon then.
okay, thank you. Okay,
Thank you
thank you
very
very
much.
much. So, thank you everyone. So, our next presentation will be from Dr. İrem Onat.
And I welcome you all to my presentation, Environmental Impact of Profile Pipe Manufacturing. First, I will talk about what life cycle assessment is, then I will explain the operation of the pipe profile production facility. After discussing the material and methods, I will dive into the characteristic of pipe used in this study. Providing information about the properties of the pipe used in this study, I will move on to inventory analysis. In section 6, I will explain the impact categories. Finally, I will discuss the scenarios and results before concluding my presentation. In the diagram, we observe the cradle-to-grave life cycle model. Arrows represent the flow of energy and materials from raw material production, energy use, transportation, waste generation to disposal. All steps are included in the cradle-to-grave life cycle model. The fundamental stages of the life cycle assessment procedure are definition of purpose and scope, inventory analysis, impact assessment, review of results. Definition of purpose and scope involves determining objective, content, and relevant choices of the study. Inventory analysis involves creating a list of the energy, materials used, and environmental emissions. Impact assessment calculates the potential impact generated by the identified inputs and emissions. Review of results involves reviewing the results obtained each stage. The production process follows these steps: slicing, form, weld, calibrate, cut, pile, delivery. Blue arrow shows materials coming in, energy used, waste, and the final product going out. Orange arrows represent the circulation of oil water mix and cooling water. In the initial slicing, large sheets are cut to the right size. In the forming, the cut sheet becomes a rolled form. Welding shapes it into a pipe. Calibrating is for making rectangular square profiles. In the cutting phase, the pipe is cut to the desired length. Lastly, cut products are stacked for shipment in the delivery. Our next topic is material and method. The study aims to evaluate and compare the environmental impact of producing three different profile pipes. Each process in the production line was truly examined and input-output inventories were determined. Gabi software was used with the EcoInvent database. Scope of this study includes the transportation of raw materials, production, and the removal of waste from the facility. Functional units. We have two different functional units. One is 1 ton of steel profile pipe production, and the other one is 1 meter of steel profile pipe product. You see a diagram representing the system boundaries. The dashed line indicates the system boundaries, and T stands for transportation. It includes the transportation of coil sheets to the facility, the production, and transportation of the lubricating oil used in the production, and the transportation of the wastes generating from the production process, as well as the management of these wastes. Additionally, no calculation were made for defective the final product and the final product shipment process. So these are the processes in the system boundaries. We see the selected pipe types in the table. 3 different pipe types were chosen, which named type 1, type 2, and type 3. Initially, a pipe was selected as type 1, so you see the specification in the table. For type 2, the pipe with a thickness double to 3 millimeter was selected, so we changed just one characteristic for each pipe. For type 3, a pipe was chosen with the same physical characteristic as type 1, but made only from a different sheet metal. So there is 2 different type of sheet materials, black coil and galvanized sheet. In the environmental impact assessment, the production of coil sheet was not included in the system boundaries because the steel profile pipes can only be produced from the steel coil sheets, and it is not a situation we can change to reduce their impact. So additionally, coil sheet production has very high values in the impact categories, making it difficult to compare with the remaining factors. For these reasons, we focus on the factors that we can control to optimize our facility. So sheet production didn't include in the project boundaries. We conducted our study in a real facility engaged in profile pipe production. We carefully determined the inputs and outputs for the crucial steps, inventory analysis. Inputs for profile pipe production can be categorized into 4 main headings: coil sheet, lubricating oil, city water, and electric energy. The outputs resulting from the pipe production include scrap, hazardous waste, and final product. For the inventory analysis, on the left side, we see the values based on the production of 1 ton of profile pipe, while on the right side, values are shown based on the production meter of profile pipe. Both sides provide the consumption distribution of 3 different profile pipe types in each category. When normalizing the values, the type 1 profile pipe was used as a reference. Input, output values for type 1 profile pipe production were considered as 100, and the percentage distribution of the other 2 profile pipes was determined according to this value. Some reasons for the difference in the consumption values according to the inventory analysis are identified. So one is an increase in the thickness creates the difficulty in the processing material, so leading more energy consumption. So when we compare the consumption results, we saw that the thickness creates difficulties to process, so it increases the energy consumption. Additionally, the rise in the thickness increases the temperature during the profile pipe production. To reduce increased temperature, more cooling water and mixture of lubricating oil are used, so the water consumption increases too. Excess thickness increases the amount of scrap generated and results in more waste during the processing. Production from the different sheet types leads to variation in energy consumption. So galvanized sheets are easier to process, so it requires less energy. In production from galvanized coil sheets, more lubricating oil is used, and due to easier processing, less waste is generated. So these are the inventory analysis results. After the inventory analysis, we can now move on to the environmental impact assessment. Let's first examine it based on the production of 1 ton of profile pipe. On the right side, we see the impact values created by the 3 profile pipe in all impact categories. On the left side, we have a visual representation of these values. A general overview of the chart indicates that type 2 profile pipe has the most significant impact among the 3 types in impact categories. In ADP fossil, acidification potential, eutrophication potential, FETP, global warming potential, human toxicity impact categories, type 2 profile pipe is followed by type 1 and type 3, respectively. In the ODP and POCP categories, type 2 profile pipe is followed by type 3 and type 5. So we can see that type 2 is the most significant impact on the environment, and type 1 and type 3 follows respectively, but in some categories type 1 is follows behind type 2. In some categories type 3 is follows behind type 2. So it depends on the impact categories. Another noticeable aspect is the negative values in first and the last impact categories. The obtained negative values results from the excluding steel production from the system boundaries, and also including the scrap waste recycling in the system boundaries. These negative values indicate a positive environmental impact actually. The total impact is negative because the steel coil sheet production is not included in the system boundaries, influencing the overall negative outcome. Now let's examine the same evaluation based on the production of 1 meter of profile pipe. It's actually same, but if we examine each impact categories by one by, we can see each category has different impact for 3 different profile pipe types. So generally the results are same, but for each type it could be different. For example, if we look at the first and the last impact categories, we can see the same result that came from the 1 ton of profile pipe production. So it's still negative because of the reason that I explained earlier, but the results are similar. In the literature, there was 2 sources were considered for comparison. So the results are similar. There is some differences, but we get the similar results from the analysis. So we can say our study is aligned with the literature. And in one source, life cycle assessment study was conducted for coated steel pipe production. The other one is for uncoated steel pipe production. So there is different values from the studies, but one is the coated, the other one is uncoated. So the value is between them most of the time. Based on our modeling, the primary components influencing the environmental impact across various categories have been recognized as electricity consumption for 3 profile types considering 2 functional units. So we can say for 3 profile types for 2 functional units in most of the categories, energy consumption is the most significant environmental impact. Therefore, to reduce the environmental impact in these categories, the use of renewable energy sources of grid electricity has been examined for these categories. The entire modeling was conducted using the grid electricity in Turkey. So we compare these values with wind and solar power. When normalizing the values, grid electricity was considered as a reference. So blue one is grid electricity, and the values generated by this usage were accepted as 100, like we did it before. The effect of the other two renewable energy sources were also determined based on these references. The gray one is solar power, the orange one is wind power. For the three types of profile pipe, a positive environmental impact was observed when both grid electricity and renewable energy sources were used in the first and the last categories. Looking at the remaining categories, it was observed that the environmental impact of wind energy is lower than the solar energy. The positive direction of the impact was noted to scrap waste recycling. So in some categories, we get positive impact that comes from the scrap-based recycling inclusion. So that is the one results from the scenarios. The last slide is our results and recommendations. When comparing the three profile type for two functional units, it is observed that the greatest impact occurs in the production of the second type of profile. So the ADP element and TET impact categories have shown environmental impact in a reducing direction for all types. And we explain these for waste recycling and not including the coil sheet production in our system boundaries. The exclusion of steel coil production from the system boundaries and the negative impact from the waste recycling resulting in the negative outcomes for these two impact categories, as I said before. For both functional units, the scrap waste recycling impact factors have been identified as the most significant component in the ADP element and the TAT environmental impact categories for all these three types. Except for the ODP environmental impact category, electricity consumption impacts have been determined as the most important component in the other remaining impact categories for, again, three profile types and two functional units. Using wind energy has the least environmental impact comparing to the grid electricity and solar energy. Choosing the wind energy over grid electricity would reduce our environmental impact, so the renewable energy is really important for us. Here is my references. Thank you for listening.
Thank you very much, Dr. İrem Onat. We have successfully completed our session 3. Next, we will be presenting the session 4. Thank you for attending.
Hayat hızla akıyor ve biz bu hızı seviyoruz. Her güne heyecanla başlıyor, her anı doya doya yaşıyoruz. İlk günkü heyecanımızla yılları aşıyoruz. Zaman akarken biz de kendimizi arıyoruz. Heyecanla, merakla. Sen de kendini mi arıyorsun? O zaman zamana yetiş. Bu sadece kendini bulmakla ilgili değil. Asıl heyecan kendini yaratmakta. Bir şeyler mi yaratmak istiyorsun? Mükemmel. Metali işlemeyi, bir bina yapmayı, bir iş kurmayı, hatta bir şehir kurmayı öğren. Hayat kurtarmak, teknoloji geliştirmek, üretmek. Hepsi burada. Ve burada tüm deneyimler profesyonellerle yan yana. Ancak hızlı ilerlemelisin. Çünkü bugün şimdi gerçekleşiyor ve yarın çok yakın. Hayatta öne geçmek istiyorsan önce zamanın önüne geçeceksin. Hep ileri gideceksin. Bu Doktor Suat İrfan Günsel. Tanıyor musun? Onun da söylediği gibi. Üniversiteler toplumların dokuma tezgahıdır. Toplumları geliştirir, dönüştürür ve gelişmesini sağlar. O burayı bugünden yarına hazırlamak için kurdu. Senin için, ileriye gitmek için. Yana ya da geriye değil. Sadece ileri. Çünkü gelecek çok yakın. Hadi harekete geç. Fikirlerin ne kadar ileride olursa yarına o kadar yaklaşırsın. Yanındakileri de geleceğe taşırsın. Bu senin geleceğin, senin fırsatın şimdi. Hadi yarın yakın. Hepimizi ileriye götür.